Welcome to lecture 16 of the course Marine Propulsion. Today we will discuss hull-propeller interaction. The key concepts covered in today's lecture will be the basic aspects of hull-propeller interaction, concepts of wake fraction, thrust identity and torque identity. In the last week, we have covered different aspects of propeller performance in open water. That means the propeller was working in uniform inflow condition without a ship in front of it, and we have estimated the intrinsic characteristics of the propeller in terms of its thrust coefficient, torque coefficient and open water efficiency. Now, for a realistic condition, the propeller should operate behind the ship for actual operations at sea, and this creates the concept of hull-propeller interaction, because the propeller has an influence on the hull and also the hull has an influence on the propeller performance. So, the first thing here is the flow field into the propeller is disturbed by the presence of the ship hull, and hence this modifies the propeller performance, and also the working of the propeller will have some effects on the ship hull. This mutual effect taken together is called hull-propeller interaction. So, in this simple diagram we have the propeller here and this is the ship hull. In addition to that, we will have the ship rudder here. This rudder is used for maneuvering the ship. So, the propeller slipstream will also have an influence on the rudder performance. Now, if we look at the different aspects of hull-propeller interaction, for example, we have the propeller and we have the ship hull. So, for the same ship hull, if we change the propeller, the powering process will be different, because different propeller designs will have different performance based on the geometric aspects of the design that we understand from the propeller theory and the open water performance discussion that we have done. Now, on the other hand, if we change the ship hull, for example, for the same propeller design, if we change the design of the hull of the ship, typically the design near the stern, which impacts the flow into the propeller, then what will happen? The flow field into the propeller will change, and because the flow field will change, the performance of the propeller will be changing. So, the aspects of hull-propeller interaction in brief will cover the impacts of the propeller on the hull performance and also the impact of the hull on the propeller performance. So, let us look into the basic aspects which are very important in defining certain parameters which will relate to the propulsion performance of the ship and propeller in unison. So, the first thing is the wake. When a body is moving in a fluid, there is a wake generated due to the geometry of the body and the flow characteristics, and this wake of the ship will define the inflow velocity into the propeller, and because the propeller is behind the ship, that inflow velocity on the propeller plane will be different from the ship speed, and that will again depend on the geometric design of the ship, typically the stern region, which impacts the local velocities in a higher way. So, VA, which is the velocity of advance for the propeller, which has been defined. For example, in open water condition, that VA was the velocity at which the propeller was moving forward. So, there was no body in front of the propeller. Now, we have a ship. So, the ship is moving forward with a speed Vs. The propeller is also attached to the ship. So, ideally it is also moving forward with a velocity Vs, because it is attached to the ship. But because of the wake field created by the ship, if we stand in the position of the propeller, so that means if we stand in the position of the propeller here and the ship is moving forward with a velocity Vs, one will see that the average velocity at the propeller plane will be different from the speed Vs at which the ship is moving forward, and it will be seen that this particular velocity Va, which is the velocity of advance defined for the propeller, will be lower than Vs, and the reasons for this will be discussed in this lecture. Now, the second action is the propeller is working behind the ship and it is accelerating the water at the stern region of the ship. Because of that, the resistance of the ship gets augmented and this resistance becomes higher than the bare hull resistance. That is why RTP, the resistance of the ship, the total resistance with a working propeller behind it, is higher than RT, where RT is the total resistance measured from the resistance test where there was no propeller. Okay. And the third is the efficiency of the propeller working in uniform flow, for example, in the open water condition, will be different to the case which is the actual condition of propeller operation behind the ship, that is non-uniform flow field. So, the efficiencies of the propeller will be different in these two different conditions. Now, if we look into these effects, the first one is the velocity of advance is lower than the ship speed, and this leads to the consideration of wake fraction. The increase of resistance due to propeller action with respect to the total resistance measured during the resistance test is taken care of by a factor called thrust reduction, and the difference in efficiency between the behind and open condition is taken care of by a factor called relative rotative efficiency. So, in this particular lecture we will cover the first point, which is the wake fraction, and we will discuss two different identities, thrust and torque identities, to calculate the effective wake fraction of a hull propeller system. Regarding the points 2 and 3, thrust reduction and relative rotative efficiency, these will be discussed in the next lecture. So, let us look into wake fraction. The flow into the propeller, as we have just seen, will be different from the flow condition in the open water condition where there was no ship. That means, the averaged inflow field into the propeller Va is less than the ship speed, and that is how we define the wake fraction. The most standard way of definition is the Taylor wake fraction defined by Admiral Taylor, where the wake fraction denoted by W is defined by the difference in speed Vs minus Va divided by the ship speed, which is taken as the reference. Because in the behind hull condition, which is the actual operation condition for a ship, the ship speed, the speed at which the ship is moving ahead, is the standard reference speed, and Va is something we do not know, that we will see how we can compute the value of Va for behind hull conditions using wake fractions. Now, in this way, the wake fraction is defined with respect to the speed of the ship as well as the advance speed Va. Now, the same way Va can be related to Vs using the value of wake fraction. So, next we will see the physics of this particular wake fraction, that means why is the difference between Vs and Va coming into the picture, what are the major causes of this particular differences. The first one, as we call, is the potential wake. If we have a body with an inflow here, so, and considered potential flow condition, the streamlines will go around the body. We are neglecting viscosity here, right. and far away the streamlines will not be affected by the presence of the body. Now, because of this, in this particular region, just in the wake of the body where we are concerned with, because the propeller is present just behind the ship hull. This particular diagram can be assumed to be a section taken at a water plane which is at any location on the propeller disc. Now, at this particular location behind the ship, the streamlines will converge, and because of that the pressure will be high at that particular location, and because of that, due to Bernoulli's effect, the velocity will be lower than the free stream velocity, and that leads to a part of the wake fraction which is called the potential wake. The next factor which has a major impact on the ship wake is the frictional wake. Now, if we try to look into the development of boundary layer on a ship, it will grow as we move from the forward of a ship to the stern. And at the location of the propeller here, the boundary layer effects will be strong because the propeller is located very close to the hull, and there can also be local separation effects. So, if we try to look at the velocity in the boundary layer, approximately the profile will be somewhat like this, where the free stream velocity is outside and the local velocity will be much lower depending on the Reynolds number, and due to that there will be a velocity deficit at the propeller plane where the boundary layer effects are strong. The third factor here is the wave wake. So, if we look into the location of the propeller behind the ship due to its motion forward at a particular speed creates a wave, and this particular wave generated by a ship, this wave pattern depends on the Froude number of the ship. Due to this wave making pattern of the ship, which is Froude number dependent, or that means it is forward speed dependent, the wave pattern will impact the particle velocities just below the wave. That means we can take the crest of the wave, or we can take a point at the trough of the wave, and below the crest and trough the particle velocities, the directions, as well as depending on the waves that are generated, the velocities will be different. Now, these create a small portion of the wake velocity and leads to the formation of wake fraction at the propeller plane. If sufficient depth of immersion is there, the portion of the wake influenced by wave is small as compared to the frictional wake and potential wake. Now, these three effects create a difference between the forward speed of the ship Vs and the speed of advance of the propeller Va. The difference is called the wake fraction, which is expressed as a non-dimensional fraction divided by the forward speed of the ship. So, there are two ways of defining wake fraction. The first one is the nominal wake fraction. That means, if we measure the velocities at the propeller plane behind the ship without the propeller being present, that can be done using flow measurement devices placed at that specific location on the propeller plane at different points. So, both radially and circumferentially we can measure the velocities at the propeller plane, so that the effect of the ship hull in modifying the flow at that particular location is calculated by measuring the velocities without the propeller itself being present. That means it is only the effect of the ship, that is called the nominal wake fraction. So, it can be measured using simple flow measurement experiments, for example using pitot tube or other flow measuring devices. The other type is called the effective wake fraction. That means when the propeller is working behind the ship, due to the action of the propeller itself, the flow field into the propeller is modified. We have seen that the propeller induces velocities. So, both axial as well as tangential induced velocities have been calculated under propeller theory. So, the propeller action itself will modify the wake velocity at that particular plane, and this is called the effective wake fraction, when the wake fraction is computed with the working propeller, and this is done in an indirect manner with the results from self propulsion tests. Now, in this connection I should mention the three basic tests which are used in naval architecture for ship powering. The first one is the resistance test, second one open water test, third one is the self propulsion test. These are done in the model scale, and these experiments are required to get the powering of the ship in the full scale. In the resistance test, we have only the ship in the model scale. In the open water test, we have only the propeller. In the self propulsion test, we have the ship plus propeller. So, a detailed discussion of these different tests with actual videos of tests will be shown in the lectures under the model tests. So, as of now this particular information is required, that in the self propulsion test we have the ship and propeller working together, and we can use thrust and torque identities, as we will discuss later in this lecture, to calculate wake fraction from the results of self propulsion test and using the open water diagram that we have already discussed in the last week. So, the different components of nominal wake are the three components, one in the axial direction, which is the most important component, and that is used for the propeller calculations, because the axial component of the wake fraction is what impacts the VA, velocity of advance of the propeller. The other two components are tangential and radial components. The tangential component is only required for calculation of unsteady propeller forces and some specific calculations, and the radial component is usually small. So, here we will look into the axial component of the nominal wake, which is along the x axis, that means along the direction of the ship motion. This diagram gives a plot of the axial component of the nominal wake fraction, that means the wake fraction without the presence of the propeller, and how it varies over the entire propeller disc. The value close to 1 is at the location where the velocity deficit is maximum, that means the blockage effect of the hull is maximum, and the value which is close to 0, that means VA will be equal to VS, where wake fraction is 0, where the flow is equal to the free stream velocity. Now, we see that in the vertical position around this zone, the blockage effect is maximum and the value of wake fraction is in the higher range, and the wake varies in both the radial as well as in the circumferential direction across the propeller plane. Now, due to the hull shape and the boundary layer effects that we have discussed, combination of both the potential and the frictional wake. The wake distribution is highly non-uniform, as we can see from this diagram. Now, appreciating the non-uniformity of wake is very essential here to understand how the propeller faces differential velocity field across the different positions on the propeller disc as the blade moves, and this leads to both radial as well as circumferential variations. So, very simply, if we take a radial line here, this entire radius is the total propeller radius, and this particular length is the radius of the boss. So, the wake is plotted only in the region where the propeller blades are operating. Now, at any radius small r, let us say here, this radius small r, as we have taken before, which is a variable radius, one can average the circumferentially varying wake at that particular radius, and we can write it as W dash r, which is the circumferentially averaged wake fraction at that particular radius. So, it will be a function of radius. I can take another radius and that value will be different, and we can use this particular value to calculate the mean nominal wake fraction, because ultimately we want one particular value to do the estimation of ship powering. So, if we calculate the wake fraction by one particular value, it should be the averaged value of the wake fraction over the entire propeller disc where the blades are located, that means between the radii RB and R. So, if we take this mean wake fraction at a radius r, the nominal mean wake fraction will be given by this expression, which is the average value calculated over the entire propeller disc. That is why it is integrated over 2 pi r, because these strips are taken at radial locations and the total circumference at any radius small r is 2 pi r, and it is integrated over the entire range from the boss to the total radius of the propeller. And finally, we have this particular value as the mean nominal wake fraction. That means, if we use an experimental apparatus, for example pitot tubes or other flow measurement device, to measure the nominal wake at different locations on the propeller disc, one can do this averaging to obtain the mean nominal wake fraction over the entire propeller blade. Now, we will move on to the effective wake fraction. That means, the wake fraction when the propeller is working behind the ship. In this particular case, we do not measure it directly, it is estimated in an indirect way. That means, we use the different identities, the thrust and torque identities, using the results of the self propulsion test and the open water test. Now, as mentioned, we will discuss these model tests separately under a different lecture for model test experiments. As of now, let us try to understand that the behind condition refers to the propeller plus ship when the propeller is working behind the ship, and the open condition refers to propeller only, which is the open water test condition, and behind condition means the self propulsion test condition, which is the actual ship operation condition, the propeller is operating behind the ship. Now, there are two identities which we normally use for estimation of effective wake. First, the thrust identity, we assume that the thrust coefficient of the propeller in behind condition is equal to the open condition, and assuming that we relate the ship speed to the VA from the open water diagram, we will see how it is done and we calculate the wake fraction. Similarly, using the torque identity, we assume the torque coefficient in the behind condition is equal to the open water torque coefficient, and we relate the ship speed to the VA in open water and calculate the wake fraction as per this particular equation that we have already seen. Now, the thrust identity and torque identity gives us slightly different values of wake fraction, and we mention it using a suffix T and Q just to relate them to the exact identity by which it is calculated. Okay. And for normal self propulsion test calculations, we use thrust identity to do ship powering calculations. Let us look into each of these identities. First, the thrust identity. Here the inputs are the thrust in the behind condition will be known. For the propeller working in behind condition, the thrust is measured and we know the propeller diameter and RPM. Using that, we can calculate KT behind, we know the equation of the thrust coefficient. Now, using this KT, we enter the open water diagram of the propeller. This diagram is basically a plot of KT, 10 kq and eta O versus J that we have already seen. So, to enter into the open water diagram, we use KT behind in the thrust identity. So, we have the value of KT by the measured value of thrust in the behind condition and using the diameter and RPM, and we enter the open water diagram. Assumption is KT open is KT behind, and for that particular case we calculate what is the J for the particular propeller. Now, what is J? J is VA by ND. Now, we can use this value of J to calculate VA because propeller N and D are known. So, we can do the calculation of effective wake fraction in this particular case by using the ship speed and the VA here, the velocity of advance of the propeller, which is calculated using thrust identity. That means, I entered the open water diagram by assuming KT in the behind condition as KT in the open. So, here we assume the thrust generated by the propeller in the open water and behind condition, its characteristics are same. So, accordingly we calculate the wake fraction using thrust identity. In the other way, which is the torque identity, we calculate the torque coefficient based on the torque of the propeller in the behind condition, the measured torque here, and we can calculate KQ behind using the standard equation for torque coefficient, and we enter the open water diagram using torque identity. That means, the value of 10 kq is now known because we assume that the propeller torque coefficient is same in the behind and open water condition. So, we multiply it by 10, get the 10 kq, and for that particular case, in a similar way we calculate the value of J at that specific point here, and that J is again given by VA, the advance speed by ND, and we can use it to calculate VA if N and D are known for that specific condition, and again the wake fraction can be calculated using the same equation with this new VA. Now, this particular VA is the VA coming from torque identity, and we can calculate the wake fraction using torque identity. So, if we sum up the concepts of thrust identity and torque identity in a very simple way, the idea for thrust identity is that the thrust generated by the propeller in the open water and behind condition is same when it is operating at the similar RPM. That means thrust in open water equal to thrust in behind at same RPM, which gives the condition of KTO equals KTB. Okay. In a similar way, the concept for torque identity can be written as torque in the open water condition is equal to the torque in the behind condition at same RPM, which implies KQO equals KQB, because the propeller is producing same torque at the same RPM if we assume torque identity. Now, either thrust identity or torque identity is required to enter into the open water diagram when we have the results of the propeller thrust and torque in the behind hull condition. So, this is how we use these two identities to compute the wake fraction and other aspects of hull propeller interaction. In the next lecture, we will discuss the other aspects of hull propeller interaction like thrust reduction and relative rotative efficiency. This will be all for today's lecture. Thank you.